Good morning, everyone. It's a pleasure to be with you again for this new webinar by the International Energy Agency. I hope you had a good weekend and you are ready to continue our deep dive in how to do energy modeling. Today's session will focus on the supply part of the energy model and the provision of primary energy, and we will have a dedicated focus to the hydrocarbons sector. So just reminding you where we are in our agenda under this capacity reinforcement program on data and statistics for Nigeria. So after week 1 on statistics and week 2 on modeling, we'll continue on modeling. So you remember that we have discussed how to try to make projections on how energy demand will evolve. And we've taken the example of the building sector, trying to anticipate how people needs for cooling services, for electricity, for heating, for cooking will evolve. Once we have done that for all the end use sector, we are able to know how much oil products will be needed, for example, how much electricity will be needed, how much fuel inputs to the power sector will be needed. And we can look at the left part of our energy model and try to see what the primary energy provision needs to be if we want to match this demand. So today we'll discuss this topic and focus on oil and gas. You will be with my colleague Zakia, that you know well as with Rebecca, our experts on energy modeling for fossil fuel supply. As usually, please raise your hand and write in the Q&A box for any question. Before handing the floor to Zakia and then to Rebecca, we would like to share with you a few general data and analysis on the oil and gas sector globally and in Africa, just to set the scene for this presentation. We just a disclaimer, we all know that oil and gas are very important topics to Nigeria, so we might have in the room people who are very expert and much more than us on oil and gas management, on resources, on the economics of this. So we hope that today's training will bring to everyone a common understanding of these key topics, and that we will also be able to provide some insights from other regions of the world. So we will discuss price and demand supply iteration in the model. We'll explain how the model for fossil fuel is structured. Then there will be more consideration on finance and economy with net present value, production profile, and investment. There will be a break for question and answers with Dakia. And in the second half, we'll discuss midstream, so refinery, and we'll discuss the very key topic of sustainability. Setting the scene on oil in Africa today. On this map, you can see the main oil producers in 2020, and Nigeria is ranking number 1. But as you would know, there are all other main producers in the continent. And if we look at consumption, we will find, looking at the top countries, approximately the same with other countries such as South Africa and other countries from Northern Africa, which are main oil consumers, and this relates to their level of development. And if we look at oil consumption per capita, we would also find some other countries such as Mauritius, which is the number 1 in that category, or countries from Southern Africa such as Namibia or Botswana, which are countries with small population, but with levels of development and of energy consumptions that makes the oil demand per capita high compared to the average in the continent. So just sharing the numbers on Nigeria. Based on our latest numbers, in 2020, Nigeria produced 1.5 million barrels a day of oil and consumed 500,000 barrels a day of oil. This was in the year just before. Looking a bit more at what Africa accounts for globally, you would see that for oil supply and for oil net trade, Africa is between 8 and 10% of the total numbers. And when it comes to oil and demand and to refinery use, you would see that Africa accounts for a smaller share, which is around 5%. Let's have a look at how things evolved in Africa over the past 2 decades. So demand has been continuously growing. So what you can see, the values you can see on the right are the value in 2010 as compared to 2000, and the value in 2018 as compared to 2010. So there's been steady increase in demand, but it's not the same story for production. In the first decade of the century, the production in Africa increased a lot, and we can see the contribution of Nigeria, Angola, and others. But in the last decade, this production decreased, and with increasing demand, the result is that exports, net exports that were increasing between 2000 and 2010 have been decreasing in the more recent decade. Looking at discoveries of resources, it's interesting to see the share of Africa in global discoveries. You can see on the left where Africa sits in the discoveries of oil, and on the right where Africa is for natural gas. And sub-Saharan Africa is the red bar, and you have North Africa in blue. So in terms of natural gas, you would see that the levels of Africa contribution to global discoveries of new resources is pretty high. And if we draw the average between 2011 and 2018, you would see that Africa has accounted for 40% of all the new gas discoveries. And this brings a lot of opportunities, of course, for exports, but also for using the resources of natural gas domestically, either for power generation or for direct industrial use, having gas as an input. Looking at the prospect for production, so of course it's very difficult to anticipate what the level of production of oil and gas will be. It depends on demand. It depends also on the resources, on the global markets. But based on analysis we conducted in the Africa Energy Outlook, we would expect for oil on the left figure the levels of production in Africa to remain the same. And we see that the contribution of Nigeria would slightly increase to more than 2 million barrels a day by 2040. But when we look at natural gas, it's a very different story again. Due to the huge discoveries and resources we just mentioned, we expect Africa to play a much stronger role in the provision of international markets for natural gas, more than doubling its current level of production by 2040. And well, the contribution of Nigeria is expected to be around the same, but you would have new players reinforcing their weight, including Mozambique and Tanzania, Egypt, and you also have large resources recently discovered in South Africa or in Senegal and Mauritania that would make Africa weighting more in natural gas export markets and production markets. So we've discussed discoveries, we've discussed production. If we look at oil and if we try to have a comprehensive analysis of the sector, upstream, midstream, and downstream, this is what it could look like. So the yellow line is expected oil production evolution in the future. So this is just what we have seen in the previous slide. We do not expect in sub-Saharan Africa the production of oil to decrease or increase, but we expect it to remain stable. So this is the upstream part. When we look downstream, we expect oil demand to more than double by 2040. And this relates to all that we've discussed in previous sessions of increasing population, of increasing urbanization, industrialization, so which will drive upwards the demand for oil in the form of oil products, for transport, maybe for power generation, and for other uses. Between this upstream production and downstream demand, we have midstream refinery sector. And on the red line, you see that, again, we would expect refinery runs to double by 2040. We know that in Nigeria, there are some huge projects, including the Dangote refinery and others, that would really help step up production of oil products in the continent. But as you can see, the refinery runs trend is not as high as the one for oil demand. So as a consequence, we would expect imports of oil products to increase, and this is the blue blank that you can see. Okay, one more analysis we like to share, and it relates to the revenues that governments are making from their resources. On this analysis, we've taken the top 10 oil and gas producers in Africa, and we have tried to look how much money the states were making from production and exports of oil and gas. What you can see is that it's highly variations are very high over a period of 2 decades, and this relates to volatility in prices. It relates to changes in volumes produced. But what can be very problematic for governments is that when you look at government public expenditure, when there are rising revenues, government expenditure increases as well. But in period where revenue decreases, it's way harder to drop some expenditure for public goals and for and more general government expenditure. So there is really a need to carefully manage the resources from oil and gas and to use them carefully in the national public budget, especially when we look at the future. We don't know how demand for oil and gas will evolve. Under a stated policy scenario we conducted in 2019, we would expect revenues in African countries to be back on a growth trajectory, but not to reach the highest level of the previous decades. And in a scenario with faster energy transition, with more energy systems moving away from the use of oil, for example, with more electrification of transport, we would see the revenues for governments to remain at levels as low as the minimum that were experienced over the past 2 decades. So this is just a key message on countries heavily relying on oil and gas need to think about diversification of their economy, need to carefully manage the resources. And just one key element we like to point out in that picture is that if demand for oil decreases, there will be an increasing competition between producers. As you may know, Middle East countries have been a large contributor to global provision. The United States, in recent years, with the development of unconventional resources, have also very much stepped up their contribution to oil production. And increasingly, there is competition in between countries to produce and to supply the markets. One key element to look at is time to market and project size, because we see that increasingly the world tends to develop quick projects with average time to markets decreasing, which means that projects which are not too long to be developed, and also projects which are of limited size rather than huge projects. So I'm stopping here with those few analyses and data we've shared, and I like to hand the floor to you, Zakia, to come back more to the modeling training itself.
Thanks a lot, Arnaud, and good morning, everyone. I hope that you're all doing well. So before we get started on the presentation, let us do some quick Menti questions. So I will just share my screen. Okay, so please connect to www.menti.com and use the code that appears on the screen, which is 60 84 48 and 8. The Menti code is 60 84 48 8. I'll give you some time to connect, and I'll also put the code in the chat box. So 60 84 48 and 8. So the first question is, what are the key parameters to take into account for supply modeling? So here we propose you 5 parameters: prices, resources, reserves, demand, and project profitability. And let us know if you strongly agree or you strongly disagree or you're in between, so you can tell us which ones you think are most important, less important. So what are the key parameters to take into account for supply modeling? I'll give you some time to reply. When you do supply modeling, which parameters are you need to take into account? So here there's no fully right answer, but there are some parameters which are very important. So it's interesting to see that most of you, so here we have 5 who said strongly agree for demand. So you think that's the first key parameter. Prices also is ranked as key, very high. Reserves, resources, it's last. It's very interesting. Very good. We have many people participating. So demand is the first one, which is very interesting and good that you think that when you do supply modeling, taking into account the demand is important, and not only the supply factors. So I think most of you got it fully understood that one of the key parameters that needs to be taken into account, it's demand and prices in addition to the supply parameters. Excellent. Let's move to the second question now. So here we are asking you for your opinion. Do you think that we are close to reaching a peak in global oil production? So here it's really, what do you think? Do you think we are very close to reach a peak in global oil production, or it's not going to happen very soon. What do you think? Here it's like 50-50 right now for those who have already replied. So are we close to reaching a peak in global oil production? So here, I think that if we, to reach a peak in global oil production, first we have to reach a peak in global oil demand. And it depends on the products. And it also depends on what are your targets to. We know that if we want to meet climate goals and all, we need to reduce fossil fuel demand. So it's interesting to see here that most of you think it's like, it's not very soon, but it's not soon at all. So it's in between. Very good. So let's move to the next question now. In your opinion, do we still need oil even in a sustainable development scenario world? So the IEA Sustainable Development Scenario, it takes into account climate goals and also about reaching net zero emissions in around 2070, around those years. So do you think that in a sustainable development scenario where we take into account the Paris Agreement goals, do you think we still need oil? So again, here it's in the middle. It's not strongly agree or not strongly disagree, but you kind of agree and disagree. More towards you agree. So, but if we look at a recent report that the IEA released not long ago, where we have a net zero scenario, in that scenario, it says that if you want to reach net zero emissions by 2050, you will need to stop new investment in fossil fuels, which is quite strong statement. But in a sustainable development scenario, we still need a bit of oil. So now let's move to the presentation. So I will do a new share.
Hello and welcome to this subsection as we talk through supply modeling and specifically fossil fuel supply modeling in the IEA's World Energy Supply Model. In the course of this first section, we're going to detail more information and background on the prices and demand supply iterations that we go through in the model. We will step through first taking a look at the current picture of the oil and gas industry today. And what you see here is a view of the ownership of oil and gas, both the proven plus probable reserves, the production, and the upstream investment by company type from 2018. On the left-hand side, we see oil, and the right-hand side, we see gas. And this is broken apart by the industry landscape for oil and gas, and it's typically characterized into the majors, producers like Shell, Total, Eni, BP, ExxonMobil, and others, independents, companies like Tullow, the North American shale independents, including Oxy and EOG, and also national oil companies that are split between both independent NOCs and NOCs that are more closely tied to the states. Fossil fuels still can provide an opportunity for energy access under the right conditions. However, increasing attention and import is being paid to reducing emissions across the sector. NOCs on the whole account for well over half of global production and an even larger share of future and existing reserves. As we take a look at the view of remaining technical recoverable resources for both oil and gas, we'll step through the picture of gas first. Currently, we have about slightly less than 20% of total resources have been produced to date with oil. And oil is broken apart into conventional, extra heavy oil and bitumen, tight oil, NGLs or natural gas liquids, and kerogen oil. On gas, much of gas is on the conventional side. Overall, we've consumed less than 20% of the oil and gas that's estimated to be developable. Significant sources and resources still remain, particularly in conventional and extra heavy oil or bitumen. And gas resources, previously thought as a waste stream many decades ago, have grown to be considered a potentially important transition fuel as we look forward to clean energy transitions. Shown here is the resource breakout for both oil and gas. And overall, there's not a question of whether there are resources to develop. The question that we're going to dive into in this slide and future slides as we go through the course of this module is at what cost and what does future demand look like, and how the balances of those two factors play into global supply. So we'll explore this in much of the discussion, but first turn to the question of emissions from oil and gas operations. Fossil fuels can provide an opportunity for energy access under the right conditions. However, increasing importance and attention is being paid to reducing emissions across this sector. In 2020, we've seen many countries, including China, Japan, and Korea, make net zero carbon emission pledges. The IEA has analyzed emissions from oil and natural gas, including a recently updated methane tracker, which shows country and regional breakouts of the primary emission pathways. For oil and natural gas production, most emissions from operations are caused by the release of methane to the atmosphere. Methane on a 100-year lifetime has approximately a 30 times greater warming potential than carbon dioxide. And we estimate, based on our analysis, that more than 70% of these methane emissions could be abated at no net cost to the operator, or essentially could be captured and sold on as methane in the existing operations. A long-time area of focus, flaring has received even greater scrutiny and attention in the last few years. In 2019, about 150 BCM of gas was flared, or more gas than is currently used by the entire continent of Africa. Flaring of associated gas occurs sometimes in the event of an emergency or a non-standard operational event. However, most flaring occurs due to the lack of a gas market or infrastructure built directly to the operation site. Recent geospatial analysis by many individuals and highlighted by the IEA indicates that more than half of flaring occurs within 20 kilometers of existing gas pipelines. Further, if flares were unlit or operating in poor conditions, even more emissions than are currently estimated may be released. We're going to step into next the IEA's World Energy Model and an overview of the supply model. As we turn to the supply model, we consider what must be taken into account in order to assess supply. Some of these key elements in the module include demand across the sectors, price, available resources, and the cost to produce those resources, or essentially the economic viability of the projects. Government policies in particular have a hand in driving demand for a product stream, as they help to drive customers and consumers or help to set future CO2 pricing, for example. The price may be sufficiently stimulating to bring in new investments into a sector, and the price and supply are intricately linked and depend on resources, production costs, and overall policies. In the World Energy Model, we assess a price scenario that maintains a relatively static path forward. In reality, prices fluctuate, and sometimes significantly. The World Energy Model assesses supply of fossil fuels, including coal, oil, and natural gas, as well as traditional as well as traditional and modern biomass. Demand is first assessed by sector and country and region, and global supply is then modeled. Import and export needs are assessed in the model, and trade is defined based on these demand needs and global excess. Typical models in the IEA World Energy Model contain 3 fossil fuel supply modules for oil, natural gas, and coal. Oil and natural gas are linked as many reservoirs contain heavier components and result in the production of natural gas liquids, or NGLs. These NGLs are incorporated then into the overall oil supply model. Oil, as a global commodity, is treated globally, such that supply and demand are in balance. And natural gas and coal seek equilibrium in the model on a regional basis and are considered with regional demand and trade infrastructure constraints, and then the supply is equilibrated. Price iterations that we'll dive into in subsequent sections are needed to ensure that the price assumptions that are inputted into the model reflect sufficient return on investment. In the model itself, we're going to look and explore more several of the different types of oil that are modeled, as well as several of the different types of gas that are modeled. In the next section, we'll talk a bit more on both these details. First, a word on price trajectories. The World Energy Model takes international fossil fuel prices and the future pathways and trajectories and reflects the levels needed for sufficient investment in supply to meet demand. Prices are derived through iterative modeling, and their trajectories, while they appear smooth, in reality are much more likely to be volatile. The cost of supply by type of resource, location, and including technology learning curves varies for both oil and gas. This also considers how the relative risk of investment changes depending on country or region. The price of oil or gas must be sufficiently high to encourage investments in supply to meet demand. Shown here, you can see the different price outlooks that were used in the World Energy Outlook in 2019. For the current policy scenario, and this scenario, in light of the COVID pandemic, was not utilized in our WEO 2020. It had reflected essentially a business case as usual that is not as applicable in the current environment. It shows the stated policy scenario or steps that reflect a pathway that takes into account all currently stated policies from governments and industry insofar as they are sufficiently detailed and robust to have a likely probability to be achieved. And then also the Sustainable Development Scenario. In this scenario, the SDS works backwards from the energy-related United Nations Sustainable Development Goals to achieve universal energy access for all, improve public health outcomes, and achieves a net zero emission by 2070 with about a 50% chance of limiting a temperature rise to 1.65 degrees. You can see the variations in oil price that are used and needed in each one of these scenarios. And while oil price varies widely, and show the smooth trajectories here, they do reflect the different ways in which resources, costs, and policies all affect the supply-demand balance. In this next section, we're going to dive deeper into the fossil fuel supply module, its structure, and its submodules. Here, we detail the project resolution in the World Energy Model, specifically in the oil supply module. In the WEM oil supply module, there are 10 distinct types of oil, some of which have finer detail than others. In the crude and enhanced oil recovery sections, or subsections, we detail further the onshore, shallow, deep, and ultra deep. Other categories, such as the Arctic, extra heavy oil and bitumen, kerogen, tight oil, all have varying distance, technology, or depth categories. Coal to liquids, gas to liquids, and additives are assessed as well if sufficient price warrants. Overall, in comparison to the electricity module, the oil module is more flexible than that of electricity, but the structure that we've seen is quite similar. When we look ahead to gas, at first blush, the gas supply module appears more simplified. Currently, we're working to break apart the modules into more discrete subsectors similar to the oil module. The conventional gas module is broken apart into gas and Arctic gas, as well as unconventional gas, including tight gas, coal bed methane, shale gas, coal to gas, and hydrates. The overall structure of the module, and we're going to highlight this on the oil supply module. It first fundamentally looks at global demand. The key inputs into the module, such as historical production levels, recently sanctioned projects, remaining technical recoverable resources, costs, including finding and development, lifting costs, or our OPEX, fiscal tax regimes, discount rates, and decline rates all help to govern what remaining or excess demand needs to be covered. The module is an equilibrium model and will assess what further supply is needed based on the excess demand and project economics. It works the economic calculations based on what you've seen in the preceding 2 slides, and it ranks those projects according to NPV. Then it brings on these new resources according to that ranking, subject to any logistical or resource constraints. This loop is then repeated for all regions and all oil types or all gas types. Moving from the basics of the demand and supply model, we're going to also dovetail and talk more on the NPV calculations and the investment portion of the model. When we think about replicating investment decisions in the oil and gas industry, we take a similar approach as what happens in industry in the module itself and in the model itself. We look at the net present value calculation at a project level, and then scale that up on both a regional and a global basis for oil and gas supply. Both the supply and investment modules are our economic models. We treat investment as the level of capital that is spent to develop or maintain assets. Net present value calculations are the basis of the model, as the model assesses the economic reward or loss of producing a set of resources. Let's first look at the variations in the economic model inputs by country and by region and also globally. Prices are assessed, as we spoke earlier on the oil side, with a global price. Gases see a different price regionally or by country, depending on scarcity and cost to transport. Countries have a different tax treatment regime, and we track those at the agency and team levels. Additionally, we assess the cost of capital per country and region and per resource type. This translates into an assessment of the investment risk in a country or region. Additionally, as we take a look at resources, we have different costs of supply that govern the outputs of the net present value calculation. And these are done based on the sub-modules and the subsectors in oil and gas that we saw in some of the preceding slides. The cost to produce these are impacted by learning, technology learning, by depletion, and also by inflation, which is in turn impacted by prices. Resource availability and trading and other constraints are also accounted for in the model as the model considers which projects to pick and select to develop in order to meet excess demand and build a view of global supply for oil and gas. Once the model has picked which projects to take forward, it then produces and makes the production profiles according to standards that we have set within the module itself, based on country and region, and also by access type or resource type. The resources selected for production are taken according to the standard profiles. These profiles are set up by reservoir type, extraction method, technology, and location. And shown here, we look at some examples from deepwater US, pre-salt deepwater Brazil, and you can see the differences there based on historical time to invest, develop, and bring on initial production. And then also an example of bitumen mining from Canada, which you can see takes some time to invest and begin production, but then has quite a slow and long plateau. These outputs are what define the production side in the supply module. Natural gas is facing a potential turning point in Africa. In North Africa, gas already meets around half of the region's energy needs. But in sub-Saharan Africa, it has thus far been a niche fuel. The share of gas in the energy mix is around 5%, or among the lowest in the world. Today, Africa accounts for about 4% of global gas demand and about 6% of global production. There are nevertheless several reasons to believe that the future of natural gas in Africa may be different from the past. In recent years, there have been a series of major discoveries in almost every part of the continent, notably in Egypt, in the Azorean adjacent fields, in East Africa, in Mozambique, in Tanzania, West Africa, in Senegal and Mauritania, and also South Africa. Between 2011 and 2018, Africa accounted for more than 40% of global gas discoveries. Together with LNG technology innovation, these developments could fit well with Africa's push for industrial growth and its need for reliable electricity supply. In the power sector, the rapid deployment of renewables leaves room for gas to grow as a flexible and dispatchable source of electricity. Outside the power sector, the successful industrialization rests upon the stable provision of energy, including for energy uses that are hard to electrify. So gas could be quite well suited to some of these needs. Much, however, will depend upon the pricing at which gas becomes available, the development of distribution networks, including small-scale LNG production, and the financing available for infrastructure. In our projections, Africa becomes a major player in natural gas as a producer, a consumer, and as an exporter. Today, Africa as a whole exports a similar volume of gas as Australia, and the continent's gas demand is similar to the combined demand of Japan and Korea. Production declines are the key determinant for future investment needs. Here, we see the historical global oil demand going up to 2018. So we're just shy of 100 million barrels. Moving to the future, if we just invest in current supply, if we do not further invest and just look at the declines from existing fields, you can see that there's still significant oil supply going out into the future for the next 2 decades. If we invest only in fields or only in existing fields, so essentially brownfield production, then we can see that with a fairly minimal amount of investment, oil production still will be maintained quite significantly through the 2020s and the 2030s. To look at the needs in the sustainable development scenario, we can see global oil demand emphasized by the top of the green line here in the sustainable development scenario. We can see that there's still a significant amount of investment that's needed in order to meet demand, even in a more sustainable scenario. If we take a look at the stated policy scenario, there's significantly more investment as well that's needed to both maintain the level of oil demand that we have seen or project to see potentially in the next 2 decades.
So I hope that you have enjoyed this first part on oil and gas modeling. So now we have been joined by my colleague Rebecca Schultz, who is an expert on supply modeling, and we will be very happy to take any questions you might have on what you have just listened now. So hi, Rebecca.
Hi, Zakia, and welcome everyone. Can you hear me okay?
Yeah.
Wonderful.
We can hear you well. So Rebecca, we already have a first question on gas flaring. So gas flaring is still high in Africa. What needs to be done to reduce this wastage?
It's a great question, and it's actually one that we're diving into in a bit more detail in our upcoming World Energy Outlook as well. So it's a question that I greatly appreciate, and one that I've been working on quite closely as well. I'd have to say that it's not just across Africa, though, that gas flaring is still quite high. We saw in the early part of this millennium, really from 2000 to 2010, we saw some real strides in reducing flaring. But in especially the last 5 years, flaring has picked up globally in many regions, including Africa. And one can talk about some of the primary reasons of lack of a gas market or an effective market for the gas to go to. But one of the key issues is that often companies and countries don't really understand who is flaring and how much and where they are flaring. And so the first thing to understand the problem is to start to measure it and start to understand the nature of the problem itself. And there are some resources that I can direct people to if they're interested. And at first, I would say that the Global Gas Flaring Reduction Initiative by the World Bank is one, and it's one of the leading areas that we point to. The data that comes from that is from the Payne Institute, associated with the Colorado School of Mines, and their data is what the World Bank uses. That data also is available, and you can take a look via Capterio. It's CAPTERIO, and perhaps I can drop the spelling into
the chat
when we're finished, or provide it to Zaki as well. They actually have the same data, and they visualized it globally, and they have now open sourced and allow you to take a view of where all the flaring is over the last years. And so you can actually pick that up, and you can look at where flaring is occurring in Africa, what sites is it occurring at, and where. And so you can dive in, locally in Nigeria, but also look around the world and see where that is as well. And then once you have an idea of where the flaring is occurring, then you can really start to understand and develop policy support to answer the question that's really specific for your area and the type of production that you have locally as well.
Thanks, Rebecca. That seems very interesting, and indeed, if you can put it in the chat box for the participants to access, that would be great. So for the participants, please, if you have any questions, take the opportunity of us having Rebecca with us now. She will also join at the end of the training to help answer more questions. But if on the first part of the video you have any question, please don't hesitate. Excellent. I see, Rebecca, you put it capterio.com flare intel.
I did. It's quite a useful site to start to visualize what's happening, because quite often, a large majority of the operators or producers can actually be quite good, but one bad operator can really create some quite negative numbers and perception for a very large area as well. So it's quite interesting to take a look at what that looks like.
Yes. So I'll just copy that also in the answers of the Q&A box. So please, if you have more questions before we continue with the rest of the presentation, don't hesitate. Oh, I see. You. Okay. No more questions. So thanks, Rebecca. So we'll continue with, we have a second question. Which African country has the largest reserve of gas?
That is a great question. And it's one that I might be able to pick up and look and answer in the next time, because I don't want to misquote it off the top of my head. And so perhaps it's something that I can pick up on.
Check while we look at the rest of the presentation, and then we can answer this question later on with the right answers. So thank you. So please keep sending us questions anytime, and then in the end, Rebecca will answer all of them. Thank you. So now
see you soon.
Yeah, thank you. So let's do some more Menti question. I'll share again my screen. So let's move on to the next question. So please connect to menti.com and use the code that appears. It's the same code as before. So 60, 84, 48, and 8. So the first question is about statistics. So when we measure inputs and outputs to a refinery, can we expect to have gains? is it possible to have output greater than input? Here we are not talking, here it's about statistics, not balances. So here we are talking in MBD, in kilotons, so in physical units. Do you think that when we measure inputs and outputs to a refinery, can we get gains? So think it's a bit subtle here. It's not in energy terms, it's when you're measuring a certain quantity in barrels or tons. Is it possible? So we see that many of you think yes, and some said no. So the right answer is, it's yes. That's why I gave you some hints about the energy terms. So in energy terms, it's not possible to have more than one you inputted in terms of energy, but in physical terms, it's possible, because when you take crude oil and you put it in a refinery and you get secondary oil products, then it's possible to have a slight gain, and not a lot, but a little bit, it's possible. So that was why the answer was yes. So next question is, it's an open-ended question here. So what can the fossil fuel supply industry do for sustainability? So what do you think the oil and gas industry do for sustainability? So this is something also that in the second part of the presentation, Rebecca will detail, but we just wanted to see if you have some idea of what the industry can do for sustainability. Curb glass flaring, rationalize consumption. Very good. So please tell us, what do you think the industry can do for sustainability? Technology advancement to improve efficiency? Yes. Limit the potential of reaching set targets for 2030 and beyond. Find more carbon friendly and efficient ways of exploiting fossil fuels. Excellent. I see that we have a lot of ideas. Invest in cleaner energy solutions, improvement of technology, diversification of end users, reduce glass flaring, encourage end use efficiency, invest in clean, blend fossil fuels with biofuels, using electric vehicles, promote clean cooking by using hybrid mixing with green fuels, curb glass flaring and technology improvement. Yes, so I see that you guys have a lot of ideas of what the industry can do to help sustainability. So this is very good. And now let's move to the presentation.
In the next section, we're going to detail and step through the refinery module in a finer detail. In the refining model, we look at the key link between oil demand and supply. The module itself is broken up into 4 steps. We're going to detail some of these further in the next slide, first on project oil demand, we carry 8 categories. And we also look at refined products demand, the overall project refinery runs, and then from these, we calculate a regional trade balance for both crude oil and for oil products. On the right-hand side, you see what we typically output for the world energy investment, looking at the refining capacity and runs by region, and in this case, from 2019's new policy scenario. First, on the oil products demand. We assess oil demand for each sector in a region from the demand modules and from those that we looked at earlier. Those are broken down for each oil product. So for ethane, naphtha, kerosene, fuel oil, LPG, gasoline, diesel, and also for other side products. There are some exceptions built within the categories, and those are for LPG, gasoline, and diesel, where we do some calculations outside and bring into the model based on different ways that some of these products are made. These are all worked and based on historical shares and also on some additional modeling that is needed in order to assess what are currently in marine bunkers and future projections for that. Diesel, gasoline, and LPG demand are worked in the road transport module and then transferred and put back into the refining module. LPG demand itself is also assessed in residential cooking and is determined by the access model. Project refined products demand takes a look further into the refinery runs, and those are modeled to meet projected demand for refined products at each product level. The refined products demand equals the refinery runs plus any processing gains. We show here the detail for total liquids, and within this, we have a buildup based on biofuels, total oil, broken apart into CTL, GTL, but also the direct use of crude oil, overall oil products, and then finally refinery products. Project refining capacity is built and assessed for 112 countries in the World Energy Model. This is built into and split into the crude distillation units and also the condensate splitters. All of these take a look at the model product yields and meet projected oil products demand on a global and also then a regional basis. Determined refinery runs or utilizations are based on regional cost competitiveness and also on product trade balances. These are pulled together, and we also take a look at the refining capacity at risk, or essentially what level of capacity may not be needed to meet current and future supply. These are taken into a regional trade balance for all of the crude oil and oil products. And we looked at the trade, and we look at the trade matrices of these and how trade can move between these different regions. The crude oil, or the refinable liquid side, looks at the crude and condensate supply. It takes this, it subtracts off the refinery intake, subtracts off the direct use of crude, and that equals the net import and export requirements. Oil products, on the other hand, look at the refinery output. They include product output from NGL, or natural gas liquid fractionation plants, subtract the oil products demand, and this looks at net import and export requirements. And these are done on a regional basis to come up with an assessment of the overall global crude oil market and also the product markets. The demand for oil products has shifted over the last several decades. The past challenge for refiners has been reducing from the bottom of the barrel. However, when we look at future demand, the challenge becomes more to increasing yields from the top of the barrel products, particularly as we look at product demands that are being pulled and used for the petrochemicals industry and for the plastics industries. In the last section of this module, we're going to take a look at the implications for sustainability in the oil and gas sector, and particularly on climate sustainability. If operated to reduce emissions, oil and gas could be an important source of energy for much of Africa and could enable Africa to take a more significant global role in oil and gas production. Increasingly, as more governments have announced carbon reduction ambitions, including China, Korea, Japan, the EU, the question of emissions, intensity of supply, and imports becomes even more important. The emissions intensity of the oil supply curve is shown here. We take a look at the estimated Scope 1 and Scope 2 emissions for the overall crude oil, condensate, and natural gas liquid production from 2018. And as we look at this, and we look at the emissions intensity of this oil supply curve, we see that emissions from operations, including flaring and methane release, as well as emissions from transport and refining, contribute to the overall Scope 1 and Scope 2 emissions from operations and transport. From this, we can also see that a relatively narrow band of production contributes an inordinately large proportion of emissions, as you look from about 85 million barrels a day and above. Extracting oil, processing it, and bringing it to consumers is an important component of global greenhouse gas emissions today. And overall, these emissions are between 10 to 30% of the full life cycle emissions intensity of oil. And turning the picture to natural gas, the same applies to natural gas. With natural gas, methane leaks to the atmosphere are by far the largest source of emissions on the journey from reservoir to consumer. Increasing attention by governments and non-government agencies have shined a light, in particular, on methane emissions. The uptick in aerial surveillance, including satellite surveillance, has helped to understand where many of the larger leaks are sourcing from. Work by the Environmental Defense Fund and several other parties has also indicated that poor flaring combustion efficiency may be a major source of methane leaks, particularly from the oil sector. These considerations, also in light of the increasing number of country ambitions to reduce carbon emissions, puts into question the need and the importance of addressing emissions in new and existing operations. Looking forward to the future, it may be the case that lower emission oil and gas may be a preferred opportunity in the global market. When we look at overall Scope 1 and 2 emissions intensity of oil and natural gas production in the Sustainable Development Scenario, we can see that methane is the #1 source of potential emission reduction and abatement. The IEA estimates that about 70% of methane can be abated at no net cost. The use of CCUS, or carbon capture, use and storage, and renewables can also help to reduce or offset emissions. Additionally, energy efficiency improvements have played a role in recent years to reduce emissions and improve efficiency and costs of oil and gas operations. Oil and gas operations on the whole account for over 4.3 million tons of CO2 equivalent released today, so nearly 15% of global greenhouse gas emissions. A large part of these emissions can be brought down relatively quickly and easily. The future is increasingly electric. However, liquids and gas still comprise over 50% of energy consumption to 2040. This also includes a role for low-carbon liquids and gases, including some biofuels and hydrogen as well. When we look in the stated policy scenario towards the end of the 2030s, we see about $1 trillion invested in liquids and gases. That's reduced in the Sustainable Development Scenario to just under $600 billion, with an increasing proportion and increasing need for low-carbon liquids and gases. Overall, as we step towards the end of this module. We're going to leave you with the following conclusions. First, modeling fossil fuel supply requires information and assumptions on reserves and resources, technologies, production profiles, costs, tax regimes, many of the parameters for the NPV calculations, and including refinery, in order to assess a full supply model. Prices are needed to balance supply and demand and help to ensure that new investment is pulled into the sector. But as we model the prices, we need an iterative approach, and real pricing may be much more volatile than the ones that we project and use in our modeling. New projects are needed to come online to offset declining production, and this is needed in both more sustainable scenarios, such as a sustainable development scenario, and also increasingly then in the stated policy scenario. Detail on primary and secondary products depend on the model requirements. The evolution of infrastructure can play a very significant role in this regard. And today, about 15% of global energy-related greenhouse gas emissions come from the process of getting oil and gas out of the ground and to consumers. Minimizing these emissions should be a first-order priority for all companies and countries. No oil and gas company will be unaffected in clean energy transitions. So every part of the industry, including national oil companies, need to consider how to respond.
So that was the end of the second part of the presentation. And if you have any questions, you can already start putting it in the Q&A box. Maybe we can take all the questions down, and we can look at the exercises now. And then when Rebecca joins, she joined already. So yeah, so let's maybe answer some questions now. We already received some in the Q&A box. So maybe Rebecca, you can take those on board already. So there was one on which African country has the largest reserve of gas. So tell us what you found out. We can't hear you. No. I still can't hear you. So she's going to connect again, and hopefully it will be fixed. So, but in the meantime, please, if you have questions, write it down so that when she joins back, we can answer all of them. And also can you speak?
Can you hear me now?
Yeah. Now,
okay.
Now it's good.
Okay, good. So to answer that question, because I wanted to go back and recheck the reserves for Mozambique and a few others that were coming in. And so it is Nigeria.
Ah, excellent.
Yeah, it is Nigeria. So Nigeria has about let's say 30% more resources that have been discovered or reserves that have been discovered than let's say the next nearest countries. But there are a few like Mozambique and others where there's been quite a bit of exploration recently, and some of the numbers are still, let's say, not fully detailed. But Nigeria is really one of the most prolific oil and gas basins and oil and gas countries that there is in all of Africa. And so it's quite rich in these resources and has been developing them for a very, very long time.
Thank you. Excellent. There was one participant who wanted you to explain a bit more on gas flaring. So if you can maybe quickly just.
Yeah, I'm curious if the person would be open to maybe asking a bit more on that question. I think I did see a question come out on oil and gas trading.
Yeah, so there's another question on oil and gas trade among African countries is very low. How can the producer countries take advantage of this, especially when the gap of oil and gas between net zero and SDS is taken into account?
It's a great question, because Africa has so much in terms of oil and gas resources, but not very much of it stays locally and helps to support local markets. And I think also alluding or answering part of the question that was asked as well, because the projections for oil and gas are quite different when it comes to the sustainable development scenario and the net zero scenario as well. As oil starts to taper off and decline quite quickly, especially as electrification in Europe and the United States starts to take hold, in China, and more electric vehicles are sold. So transport demand really starts to decline. But gas historically has been thought of as a potentially very clean energy source because it burns much more cleanly than coal does. The other side of that, though, is that during the production side, gas, and in many countries, but not all countries, in many countries, there is a lot of accidental leaks and venting that occurs that actually makes gas in the upstream supply process much more, let's say, much more climate harmful and creates much more emissions than coal does, for example. Once it's burned, it's quite a different story. And so for many of the development banks around the world, they've started to reconsider the role of natural gas as being a clean energy source. And I think this in particular is an important point when it comes to some African countries and the future that they start to consider when they're investing in long-term energy sources and supplies for their local markets. The most natural thing would be to start to create those gas markets to be able to supply what we have locally and start to funnel more of that associated gas that's flared in many areas, and to start to funnel that into local gas supply as well. But I'm curious to see from the person that also asked the question on flaring, if that was the direction that they're curious to go to, or if there's something maybe a bit other that we can answer in response to that. On the trade side, I would be very curious and open to some further actual discussion on this with the person that asked, because it's really one of those questions that's very difficult when it comes to answer in an individual sense, because it takes quite a network and buildup of the market, both locally and regionally, in order to support some of that gas supply coming in.
Thank you. Thanks, Rebecca. So if Mr. Ibrahim Sulu would like to take the floor and maybe expand a bit more the discussion on oil and gas trade.
It's a very good discussion.
Yeah, so please don't hesitate. We have two persons who raised their hands. So Mr. Ibrahim Sulu. So I just gave you the possibility to speak.
Thank you very much. My question, we can forget about the last part of it on net zero and sustainable development. I think it's a mix-up. Yes, but the focus is on the low trade of oil and gas between African countries. 2011, 2012, I did a paper for my superior. And in that process, I went to the website of the EP to get information. I discovered that all our pipelines are facing north, meaning going to Europe. So the trade percentage-wise then, that was 10 years ago, is about 6% in the African trade, while all other ones are for exports. So what can we do from other regional experiences to boost the inter-African trade of oil and gas? We still need it locally, not minding all different scenarios of net zero or sustainable development. Our consumption of oil and gas, is still very important to our development. So, this is the essence of the question. Thank you.
Ibrahim, that helps a lot to clarify the question and where you're coming from. Initially, when I was talking about flaring, we talked a lot about measuring and understanding in order to reduce flaring. And countries like Norway, for example, are a good example of that. And Canada, I think, has some good precedents there as well. But I'll use the analogy of Saudi Arabia for a few minutes, because Saudi Arabia is quite interesting in that it's a very, very large producer. But many years ago, about 20 years ago, it actually started to invest in its associated gas market. And it created industrial centers and hubs that where some of the gas goes to, where some of the gas is actually steered and goes to. So it did two things. It started to measure and understand where some of the flaring was, but it also created those natural gas markets. And so it was really the demand creation and the policy side of that helped to support that connection on the supply side for the gas to really go to. And then the question then locally on a country level, but then also a regional level, is how can those demand side policies come into place and be supported to really be able to find an effective outlet for that gas. And in some areas, some very important needs for that gas and those energy sources as well.
Thanks, Rebecca. So we have Mr. Ahmad Amin also, who raised his hand. Would you like to say something?
Hello.
Hi, Ahmad.
Yeah. My question is to do with the gas reserves we have in Nigeria. From our latest data, we have about 172 trillion cubic feet of gas. Mm-hmm. And the irony is, I don't know what IEA is doing to the Nigerian government. Are you advising the government to come and start thinking about tapping the gas resources we have in Nigeria, looking at the number of people we have who are very poor? This is my question.
I'm so sorry. Can you ask can you repeat that last part of your question a little bit?
Going by the vast gas reserve we have in Nigeria, I want you to give advice to the Nigerian government. Why can't you give them advice to come and start tapping the gas resources so that it will help in alleviating the poverty situation in the country?
Yeah. So in order to have, so I support that comment, that question, because the basics of all economic growth are available energy sources, and preferably clean energy sources as well. Yes. And so I fully support that.
It's true that through when we did the Africa Energy Outlook in 2019, we look a bit at this, but we will again have another Sub-Saharan Africa Energy Outlook that will come out next year. So this is something which we might discuss internally to see if we can have something on that in the report as well.
Okay, thank you very much.
Thank you.
Yep.
So do you have any more questions, please don't hesitate. No more questions? If not, then I think we can move on with the exercise part now. So I will share again my screen. So normally, very quickly, in the booklet, you were asked you have the exercise on the fossil fuel supply, and in this exercise you have been asked to analyze the oil upstream and midstream sector, as the Ministry of Energy wants to anticipate future developments of production, refining, and trade. So we provided you with this simplified model in Excel to help you with the task. And here you have to note the below features and simplifications that we have done. So your country is a producer of crude oil, and there are several refineries producing oil products. All domestic crude oil production is directed to the national refineries, and refineries are receiving both the domestically produced crude oil and imported crude oil. And we consider here only one oil product, which is gasoline. and the refineries' outputs are not sufficient to meet all national demand for gasoline, so there are some imports of gasoline. And before making projections on the future imports and domestic production, we will first try to understand the historical data. So now I will just share the Excel file so that it's easier for us to look at the work itself. So here you are provided with the historical data for domestic production, imports of crude oil, imports of gasoline, oil demand for gasoline, refinery output. All of these are in kiloton of oil equivalent. And then you have the refinery capacity in KBD and the conversion factor from KTOE to KBD. And the first question is calculate the crude oil inputs to refineries from 2000 to 2018, knowing that the refinery losses are at 5%. So here for refinery losses, we can put 5% everywhere from 2000 to 2018. And we are asked to calculate the crude oil input to refineries. So here, what do? We know that the crude oil inputs to refineries, it can be calculated as the ratio of the refinery output, which is given in the line 13, divided by the efficiency, which is by excluding the losses. So here what we do for 2000 is that we take the amount of refinery output in the row D13 and we divide it by 1 minus 5%, and that would give us the crude oil inputs, and you apply the same formula up to 2018. So the second question was calculate the refinery capacity factor over 2018. And here, how do we calculate the refinery capacity factor? It's calculated as the ratio between the refinery output divided by the refinery capacity. And here you have to take into account the fact that the units is different. So you have to convert KTOE into KBD. So here for 2000, the refinery capacity factor, you take the amount of refinery output, you divide it by your refinery capacity, but you have to convert it in the same unit. So you also need to divide your refinery capacity by the conversion factor from KTOE to KBD. That would give you 60%. And you apply the same formula for all the years here, and you get your refinery capacity factor. So then the question 3 was calculate the total imports. So here we have to calculate the total imports and deduct import dependency both for historical years and 2019 to 2030. So here we have to do several steps. First, we will calculate the refinery. First, you calculate the gasoline imports by taking the following assumption. We know that for the refinery capacity grows at 0.10 KBD per year. So here in W30, you would increase it by 0.10 up to 2030. So every year it increases by 0.10 KBD. Then you know that your refinery capacity factor grows linearly to 70% by 2030. So in 2030, your refinery capacity factor is fixed to 70%. So what you have to do is that from 2019, you know the amounts for 2000 to 2018, from above here, we calculated. But for from 2019 to 2030, you have to make it grow linearly to 70%. So here you have the formula of how to calculate it. You take the previous year, so you take the amount in 2018 and you plus the amount of 70. So you take 2030 minus 2018, and then you divide it by the number of years and you make it grow linearly. So that was the first calculation that you do. So once we have projected the future values of refinery capacities and refinery capacity factors based on the assumptions, we can now deduct the refinery output. So what is the refinery output? It's for 2030, for example, it's the amount of capacity times the refinery capacity factor divided by the conversion. So you know your refinery output for all the years here, you can calculate it. And you know your refinery capacity output, you know your oil demand for gasoline, so you can deduct how much you are importing. You know your demand, you know your refinery output, and the difference is imports. So you can now calculate the imports for gasoline up to 2030. So that was for gasoline. Now we can do the same for crude oil imports. So you know that so the second part is calculate crude oil imports, taking the following assumption: refinery losses decrease to 3% in 2030, and domestic production of crude oil increase by 5% to 2030. So for crude oil, you know that you remember in the beginning we said that the losses were 5%, but now we say that by 2030 it decreased to 3%. So here we will have to make it linearly decline to 3% by making a linear calculation here. And your refinery inputs, you know, you can calculate it as well, because you know your refinery output, you know your refinery losses, which is 3%, for example, in 2030, and you can back calculate your input. Same for all the years here. You can take your output and you divide by 1 minus your refinery losses. You can back calculate your input. And again, here you can calculate your domestic production, because you know that domestic production decreases to 5% in through to 2030. So every year it decreases by 5%. So you take the previous year and you multiply by 1 plus 5%. It increases by 5%, sorry, every year. So you increase it linearly every year by 5%. Previous year plus times 1 plus 5%. So you have your refinery inputs, you have your domestic production, and you can now calculate your imports of crude oil, which is your refinery inputs minus how much you put into your refineries minus how much you produced, and that would give you the amount of imports of crude oil, so that you can calculate for all the years. And now we have done the calculation for gasoline, we have done the calculation for crude oil. Now we can calculate the total imports, which is the sum of gasoline plus crude oil imports. You sum the two for all the years up to 2030, you get the amount of total imports. With that, you can calculate now your import dependency. And the import dependency, it's the ratio of imports divided by the total demand. So for example, for 2030, it's the amount of total oil imports divided by your AH36, your refinery inputs, plus AH11, which was plus your refinery your total oil demand for gas. And that would give you your import dependency. And the last question, it's calculate the additional annual crude oil capacity that needs to come online. So here you have to first calculate how much crude oil production from 2018 fields will come online in the coming years. So here you have to calculate W, where's W, sorry. So W44 to AH 45. So these, then you have to calculate those, then deduct the required additions of gross crude oil production. Then you have to deduct this. So here the gross crude oil production additions over 2019 to 2030, it's your total domestic production minus your remaining crude oil production, which gives you the additions. And here we are given the production profile of the crude oil of 2018 production. And so the line, so we know this. And we also know that the 2018 production quantities. So here we know the production quantities here for 2018, you know. And so we can deduct the amount of the values for the future oil production from 2018 production. Then as we know that future total domestic production of crude oil. So here we know the amount of crude oil production. So here, then we can deduct how much production needs to come online from new fields added to the 2018 remaining production. So that was more or less the exercise. I think that just speaking like that, it's a bit more complicated when you follow the instruction in the booklet and you look at the Excel file. It's easier to do it step by step with all the hints that we provide. And we really recommend you to try to work it out. It's quite easy, the exercise. You just need to follow step by step and let yourself be guided. So that was the exercise. I don't know if you have any more questions for us, for me and Rebecca. We have two people who have raised their hands. Just give me a second. So Mr. Ibrahim and Mr. Kabir Abdul Karim. So please let us know if you have a question.
Yes, please. My question is on your Menti question.
Yes.
Can you hear me?
Yes.
Hello.
Yes, we can hear you.
Can you hear me?
Yes.
On the Menti question you asked concerning refinery inputs and outputs.
Yes.
Possibility that the output.
Yes, so the question was, is it possible to have more output than input in a refinery? And we said that in physical terms, so in barrels, that's possible. That, for example, you put 100 KBD in a refinery and you get 101 secondary products out of the refinery. That's because when you create, I don't know how to explain it in a clear way, but when you create the gasoline, diesel, and all, it's possible that you end up with a bit more in physical terms, but not in energy terms.
Yes.
So
yes.
Yeah, so
the answer is possible. That is possible. But yes. What are the risks? You didn't give the risks.
What are
Is it because of impurity or what? The reasons for the slight difference.
I think it's
what accounts for that.
Yeah, I think it's also because of densities and all. I don't know if Rebecca, you can explain it in a better way, but it depends from crude oil and you create lighter products. Yeah.
Yeah, no, that's exactly it. Essentially, as you separate out the heavier products, depending on the input makeup of your crude, you may end up that you actually have an increased volume of lighter end products that you can then sell. But that's very much dependent on the type of crude that you're producing from, and also dependent on the setup of the refinery itself and how it's cracking down those products. But it's not that it's Zakia had touched as well that energetically it's negative, but in terms of volumes and densities, then you can end up with where you have lighter end products and essentially, you've got a larger volume of lighter end products at the end of the process than you had at the beginning of the process.
Exactly. And here we are really talking about small amounts. It's not like you can double it, or it's really if you take the amount, if you put 100, you can end with 101, 105, but not more than that. Usually it's quite small, the addition.
Yeah, and you're primarily looking at your very, very light end products. So you're looking at your propanes and.
Exactly. So I don't know if Mr. Kabir Abdul Karim, you have a question? You raise your hand. No? Mr. Abdul Karim, do you have a question? Otherwise, we have a question in the Q&A box, Rebecca. What means have been deployed to handle refinery waste? So I don't know if it's clear enough. So what are the means that can be deployed to handle refinery waste?
I'm curious, I'm going to answer this one perhaps a bit on the water side, but I'm not sure if Peter is asking with reference to more oil and gas waste, or to water waste, or to energy waste and heat waste itself. I'll start on the last part of that first, because it's quite interesting. If you look at the industrial side of the oil and gas sector, especially along refineries, they have done the most in the last decade to really push energy efficiency by helping to make heat exchangers and other aspects of the overall refining process much more efficient. And we've talked internally that there's probably some more ways in which actually the oil and gas sector can help to teach other parts of industry on how to reduce their overall energy waste or increase their energy efficiency from that side. There's several other waste streams associated with oil and gas refining. Water in one is particular, and so treatment of water is one that has received and continues to rightly receive a great deal of support and attention, because getting to potable water, drinkable water, for example, from waste streams can be quite difficult, as if there are trace amounts of oil or petroleum still in that. But I'm not sure that's what Peter was asking, if we're talking more about water, if we're talking about oil and other aspects of that.
Yeah, so if Mr. Peter Akato can give more information on the question. Can you clarify a bit more your question? So in the meantime, if other participants have questions, please let us know. We have Mr. Ahmad Amin who would like to take the floor. Hello.
Hello. Can you hear me?
Yes, we can hear you.
I want to know the difference between light crude and the heavy crude and how they impact on the roasting processes in the refineries.
Okay.
So heavy crude and light crude typically has, just to check, Ahmad, you're familiar with, are you familiar with the API classification for crude as well? Because that would be what I would reference to. But if you're not as familiar with that one, then I can talk about it a bit in more general terms as well. According to essentially the API definition for density, then heavier crudes are those that are below about 18 to 20 API. Lighter crudes go up to around 40, 45 for extremely light crudes like those that are seen out of West Texas. And essentially those are going into condensates. The heavier crudes end up being much more difficult to process, in part because they tend to be much more dense. And so the rheology, essentially the viscosity of these are more difficult. You need a lot more heat to go into the process to start to break them up and to utilize the different types of processes and cracking processes that are needed. And quite often, as you get into some of the heavier crudes, they are not always, but quite often they can also have some more impurities associated with them. So higher sulfur contents and things that require more specialized, more energy intensive equipment in order to refine into the products that are then shipped globally as well. So the lighter, not to say always, but it tends to be that the lighter your products, the easier they are to process and to work into a state where they can be saleable. The heavier ones of those just need much more energy and different types of processes associated with them in order to get them into a place that they can be sold. They do end up with a wider variety of types of products, though, that can be sold as well. And so while they're more energy intensive, there is a bit of breadth around that as well.
Thank you very much. Thank you very much.
Thank you.
Thank you. It's a great question.
Yeah.
They're all great questions.
So if anyone else would like to ask any more questions, we have a few more minutes before closing the session. Please don't hesitate. Then I guess if we don't have any more questions, we can close up the session for today. So Rebecca, thanks a lot for accompanying me today and answering all the questions. That was great. And thank you to all participants for attending the whole session. I hope that it was very useful to you, and especially for Nigeria, which is a big producer. So I hope that would be helpful to your work, and see you tomorrow for the next modeling session done with the external people. So have a nice afternoon, everyone, and bye. Thank you.
Thank you so much.